Okay, so hello everyone. We will be looking through the code of the field reconciliation sets PR, which was a part of the Erlay PR, and we'll be looking through the core implementation of the code today, which is the transaction reconciliation.cpp and its tests. So we are gonna see it in VS Code. So this is the code of transition. This is the core code that has been written. There were a few commits that were pushed in the recent days. So we're also gonna focus on that. First of all, this files header are written in transaction reconciliation.h, and there are unit tests written for it, which we'll go through, and we'll also run them if possible. So this is the start of the code. So there are some uh, constants that are used for tagged hashing the CSF hasher, and there are also these constants. Const XPR means these are constants for the compile time constants. So they are gonna be constants while the code is compiling and not while it is being like used in runtime. So we have this constant is used for how many of the peers we are gonna fan out to in our incoming connections. So we have set a fraction of 0.1. So 10% of the peers are gonna be fan outed, and for outbound connections, we are gonna fan out to all the connections. We have a maximum number of transactions for which we are gonna store the fan out targets. So for maximum of 3000 transactions, we are gonna store the fan out targets. This is the salt calculation function. So this just uses the CSF hasher with the minimum salt here and the maximum salt here, and we get a SHA-256 hash of this. This computes the salt where salt1 and salt2 are given by us and the other peer we are connecting to. And we have this transaction reconciliation state class. This is used to track what is the state of the reconciliation with the peer that we have the state for, and we have some variables here. First, if it is an incoming connection or an outgoing connection, this is stored in here. So if we initiate, it is an outgoing connection, and if we don't, it is an incoming connection. These values are stored stored here, which are going to be used as salts whenever we require. We have this local set with the witness transaction IDs and the sorted transaction ID hasher, and we have the short transaction ID and the witness transaction ID mapping here. We also have this transaction reconciliation state constructor that we can use to create transaction reconciliation states, and we have a compute short ID function as defined in the BIP. So yeah, we have a mutex also here. So since these it's gonna be run parallelly with many peers, we must have a mutex in place, and for every transaction tracker we are gonna have a mutex. So, and this is the reconciliation version we are gonna use with the other peers, and these are the states that we are gonna store for the other peers, and this is the count of the inbound connections that we have currently, and this is the queue for witness transactions IDs. which we are gonna fan out and not gonna reconcile. This code, yeah, this piece of code has the witness transaction ID to node ID map. So which witness transaction IDs are we are gonna like fan out to which of the node IDs this is gonna be stored here. So we have a CSP hasher initializer, and we have a get peer state function. So this is called when we are gonna have to require the state of the peer currently with us. So we assert that there is a lock held. We have a state or salt variable here. So if we don't have anything, like we can't find this state or sort in the states states variable, we are going to return a null pointer. And if we do have something, then we are going to return the transaction reconciliation state. And the need of this function is because when we are registering the peer, if we would have like stored in register peer itself, we wouldn't have been able to like start the process of registering the peer, because we are supposed to have a remote sort from the other peer. So if we are gonna calculate the sort in there, we wouldn't have been able to like start the registration process. So this function is crucial to initiate the reconciliation process, as this returns the local sort that we are gonna create, and that we are gonna give to the other peer. And the implementation as goes as we should have a lock in place, and we should have like, we assert that there should not be a lock held before we are like accessing this function. Then we lock the mutex, and then we are gonna, this is just a print statement, and we are assuming that this is gonna be called once per peer. And so we don't have a check here, because this assume keyword that we use takes care of the fact that if there is like another uh, peer ID to local state for this year, this function is gonna fail. So assume takes care of that, and we then return the local sort that we generate. And after we give the local sort, the other peer registers. First, it also has to call the pre-register peer, and then ultimately it calls the register peer again, and then we get a reconciliation register result from the register peer. We assume here also the lock is not held before we are accessing this function. We log the mutex, and then we find the state that we previously stored in this pre-register function here. So if we don't have a state for this peer, this means that the peer has not been pre-registered before, and we are going to return a result of not found, that we don't have this peer in our states of the peer we are reconciling with. And if we do have a state, and we have a holds alternative this holds alternative function here. So the reconciliation state implementation goes as we are gonna store two things in here. We first store if we have a salt. So if we have a salt, we are gonna store a sort in here, and after this registration process, we store this transaction reconciliation state instead of that local sort. And so this function checks for if we already have a state for that. We return with the response that this peer has already been registered, and register called for this peer. We create a local sort. We get a local sort from the pre-registered state we created, and we get the reconciliation version from the peer. So if the reconciliation version is less than 1, which is currently 1 because this is the first implementation of this protocol. So 1 is the least version that we should expect. So if the reconciliation version is less than 1, then we have in reconciliation version, and we return a protocol violation since the reconciliation version is not supported as of now. We do have a print statement again, which is just prints on the terminal that we have registered this peer. We now then store the full sort in place of the local sort. We compute the sort by giving it in parameters the local sort and remote sort that we got from the other peer. We create a new state with the transaction reconciliation state class. So we have if is inbound peer to check for the connectivity, if it is outgoing or an incoming connection. We have these full sorts, 64-bit intervals. So first 64 bits are gonna be replaced first, and another 64 bits is used for the short ID transaction calculations. And then what we do is we erase the state that we generated from the pre-register function, and then we move this new state that we have created into that mstates variable. And this is a check for if the peer is our inbound connection and we have reached the maximum limits for the inbound connections that we have. We just increment the inbounds count variable to just take into account that we have added another incoming connection which we are gonna reconcile with, and then we return a success state after the function ends. So now these two functions are added from the recent commits. This function is for developer purposes. We are checking for the collisions in the short transaction IDs. That is because the witness transaction IDs are 32 bytes in size, and the short transaction IDs are 32 bits in size. So since we are reducing the size of the transaction IDs, we are sure to have some collisions where two witness transaction IDs or more may have the same short transaction IDs, and this is very true in a lot of cases. So this function is to check for such cases, and it goes as this returns a boolean if there is a collision or not. So first we just check if the lock is held or not. We lock the function, we lock the mutex, sorry, and then we check for the peer state. So if there is no state, this means that the peer has not been pre-registered or registered with us. So return a false. And then we call a hash collision internal function with the peer state that the WTX ID we are checking with the collision uh, WTX ID and the short TX ID that we are getting from both of these, one of these or both of these WTX IDs. So we just make sure that the lock is held. We compute the short TX ID from the peer state compute short ID function. We iterate over the mappings of short TX IDs to find if there is this short TX ID already in place. So if this does not result in true, which means that we have been able to find a mapping where this short ID is being used. This means that there is a collision for this WTX ID and we return true, otherwise just we return false. So this is how we check for the collision in this, and then this is this function is to add this WTX ID in this peers set, that sketch we are going to use for transaction reconciliation. So we just get the state of the peer. If there is no like state we couldn't find, which means the peer hasn't registered with us, we just return a failed result. And then if we are able to find this WTX ID in this peer's local state, then we just add this function that this WTX ID has already been added in this peer state, local state, and that this has succeeded. So if it is not already in place, we check for collisions with this WTX ID. So we have two variables of WTX ID collision and short TX ID. So we just check internally if there is a collision. If we get true from this function, we return that there is a collision in place. Otherwise, we just add it to the mapping. And if the limit is reached, so there is a limit of this 3000 in the amount of transactions that we can add for the transaction reconciliation set, because if there is no such limit, the sketch computations can go out of bounds and we won't be able to extract short TX IDs from it. So there is a upper bound for that, and we result in a failure if we have breached that upper limit. And we then add the WTX ID in this peer state's local set and just print that we have added it successfully and that the addition has been success. So the same procedure we follow here, but for removing from set, we check if the peer is registered with us, and this checks for we were able to erase WTX ID. So if this if we were able to erase from the local set, this would result in any number that would be greater than 0, and that is automatically like used as true in C++. Any number greater than 0 is in Boolean termed as true, and 0 is used for false. So this is just a syntactical sugar kind of thing. So if we were able to successfully remove it, we just also remove it from our mapping and then print it. And if we were unsuccessful in our attempt, we would just return that we were not able to remove it and then return the removed boolean. So yeah, we then, this is a function to forget a peer. So there can be many instances where we would like to forget peers. So suppose if the peer is offline for too long, we would like to add a new peer in place of that old peer, and this function can be used for that. We just check if the peer is with us in the state variables, and if we don't have the peer, which means that we might have already removed it, or it might not have registered with us at all. So we get a registered boolean. So if the peer is registered with us with the transaction reconciliation state in the local set, and that we were not the one to initiate the reconciliation, we would just decrement the count of the inbound reconciliation peers. We erase that peer and then have a debug statement or a log statement in our terminal. So this is just is peer registered state. This just checks if there is a alternative uh, for the local sort that we would have in the state. So if there is an alternative, that means that the peer has registered, and that it would like give the result of that. Now is fan out target is a function that we use to check if that the peer should be able to should be the fan out target or is a fan out target. So we have already a CSF hasher, and we just initialize it with the witness transaction ID that we are gonna have. So this generally means that this function has the parameters wtxid peer id, and this so this means that we are gonna have some peers that we're gonna reconcile this wtxid with. So if we are not gonna reconcile with this peer and we are gonna fan out it, then this function should return true, and this is just an implementation of that. So there is we are gonna use this target size that we are gonna have. So this just uses two variables. One is from this wtxid hash, what the hash digest we got from this CSF hasher, and then we AND it with this number, and then with the number of peers that we are gonna have, or this double N stand for the number of peers. So we just are gonna use some of the best peers that we have. So the way we organize the best peers are, we are gonna store them in the start of the peer list. So it goes from like best peers to worst peer. So we are just gonna initialize a best peers from this array. We have this best peers. We are initializing the size for this. So initially we include the size of the M state. So the number of peers that we are reconciling with is initially the number of best peers we are gonna have the size for. Then we get the current states of all the peers from the M states, and we are gonna just initialize it with the hash key and an index state first. So we are gonna sort the best pairs uh, according to the hash key. I'm not sure why we are doing this uh, for like sorting the best pairs array, but this is the this is the variable we are sorting on based off. So this might be a like an indicator for if that pair is a good pair or a bad pair. So this just sorts the pair in best pairs in the ascending order. We decrease the size to the target size that we are gonna have. So the best initial pairs are gonna get stayed in the best pair array. And now we have a new fan out candidates array, and we store the node IDs in this new fan out candidates array from this best pairs. Then we sort this also in terms of node IDs, and then we are gonna find if if we can find this pair in our new fan out candidates. So if we are able to find the pair, this means that this pair is eligible for fan outing the transaction, fan outing this witness transaction ID. So we are using cache here to have the number of these transactions. So we had a variable we were storing for the number of transactions that we would like to fan out, and we store it in a cache like structure. So the cache we are using in for documentation is least recently used. So the transaction IDs that are gonna be used frequently are gonna be in the back of the this structure that we created to store the transaction IDs, and the ones that are not very oftenly used are gonna remain in the front. And the process goes like, if we are having a new transaction to store in this container, we are going to remove that transaction that we are least using, and then pop this one into the container that we have for the fan out transaction candidates. And this is what happens in this piece of code. And then we return the variable if we found this to be eligible fan out target. So this variable, this function is for calculating if we should fan out to. So this just is a benchmark function that we also looked into previously in our previous review club. So we are going to skip this piece. And the another function that was added is this sort pairs by fewest parents. So also this one we discussed in our previous review series, where we would like to fan out all the transactions that have parents because of some issues that there might be race conditions in which of is being added or the children is being added. So to avoid that, we are sorting the pairs with the fewest parents, and the pairs with the fewest parents we are gonna reconcile with. And if the pair has a lot of parents, then we are gonna fan out the transaction ID for that pair. So we just go through the standard procedure, check the logs, and we have a parent per pair array. So we generally include this. First, we generally conclude that initially there are no parents for this pair, and just store it in this. And now for all the parents per pair, we are going to check for the states, which we have stored for many pairs. And if we found the peer in a state with this uh, witness transaction ID, we come to the conclusion that there is a parent for this peer, and then we add the parent count. Since the parent count is the first thing in this array, the array is going to be sorted according to the number of parents in an ascending order, and then we create another array with only the node IDs, and then we return this node ID array in a sorted fashion. So these are the functions that we have for this core implementation. And now we have the unit tests for these functions. We have a boost fixture test suite for creating unit tests for a Bitcoin transaction, Bitcoin related things. So we just have to start with this basic setup, and this is the first line that we are gonna add, and then we create these tests that we are gonna use to check these functions if they are behaving properly. So we are gonna use GDB debugger to test these boost library test cases generated using boost library. So when you are like testing using this GDB debug, you should have all these CPP files that we would like to test in an executable format. So if we look into this source code of Bitcoin in the test folder, we would see that there is a test Bitcoin executable file in here. So this file is can be compiled when we are compiling the Bitcoin core repository, and this file has all the object files for all the tests that we are going to run in this unit test cases, and we can run all these tests without any hurdles, because this test Bitcoin, when this is being created, it creates an executable for all these test files that we have. So to run this, we just use the GDB debugger. So if I would like to run this test, so first I would like to run the GDB debugger for it. So I just run the GDB with the location of the executable file. So I just use GDB with this, and this will create an executable element for me to test all the functions that we would like to run for this, like all the functions that we would like to run in this CPP file. So let's just say I would like to run this register peer test. I would just run the command. Yeah, so this like executed perfectly without any errors. So this means that there are no errors in the function. So though there are no errors, that are in this test that we executed currently, and all this function, the register peer test function, is behaving correctly as it is supposed to be, we can just use this command with any function that we would like to test. So let's just say we want to run this test for forget peer test. We would just use it again. We will just run it again with this test name. We just write this test name for, and then we can just check again that this executed perfectly. So this test is also running equally fine, and now they are, in this way we can just test all the tests we have in here. So we are gonna now look into the test files. Like we would be looking into only some of the test files. So yeah, let's just look into this register peer test. So we are preparing a peer for reconciliation. We register a peer with this node ID 0, and we just check if we pass it with the reconciliation version 0, it should return with a protocol violation. And if this passes, we require that the peer is not registered previously, and then when we register a peer again, we should return with a success. And if the peer, and then check if the peer is registered here with the tracker. Also, we would check again for peer number 1 with the node ID 1, and then do it again, and it should be success for the peers. So if the reconciliation version is higher than ours, we should be able to like register this also, because the limitation is just for the lower version. So the peer that we are reconciling with should not have a lower version, but it should not have a version that is now not supported. So it should return a success also. Also, if we try to register again with the peer, we should get an already registered response, and if there is no registration, then we should get a not found response for test. And since this is happening, like the test function normally, this test passed without any errors. Yeah, like you can also check these functions also if you would like to. The PR is still in progress, and it now also got the PR now also got into a draft mode. So there are gonna be a lot of additions we're gonna have to this PR, and there are a lot of opportunity to review many things in this PR. So like look out for more PR changes that can happen in this PR. And now we can now just look into the we can just now look into the tests or the questions that we have for this this peer review club. Yeah, so first question is why are we using the Boost library in C++ and not the Python library that we used for the functional tests. So if anybody would like to answer that.
I guess to just be able to test that module itself and make sure the functions have the right behavior.
Yeah, so we are using the Boost library only just to test the functioning of the code that we have written in the C++. The functional tests are used just for to check if the other pieces of code are functioning or like are interoperable with each other. And this is just to like sanity test our functions that we might have written in our C++ code, while in functional test would be tests that we would use just before production to test if all the pieces that we have are working correctly and in tandem. Yes.
Makes sense.
Yeah, so functional test versus unit test is also like discussed. Yeah, so the question is that the max size for the WTXIDs and also the number of peers for fan out are currently capped at 3000. There is not a particular reason given for this apart from just like that they are testing with this particular number, but where this particular number came from is not very clear. So if anybody has an idea on why this number or like why not more or why not less of these numbers.
I'm not sure either why they chose that number. I'm just checking the bit if they have any more details regarding this.
Like in the BIP, they mentioned that they tested in some kind of real world scenario by simulating a real world scenario, and these numbers are just what they find comfortable in that particular condition they like created. But I don't think that this number is the study. Yeah, like is not what they have in mind when they will be releasing this code, like in some versions of the Bitcoin code.
You mean to say that, like, since this original PR author wrote it many years ago, that number would not still be applicable now because of the recent changes in code?
Yeah, they mentioned in that BIP only that they just to check if Erlay is like having the performance that it like talks of giving. They generated an environment to test this, the fan out and the earlies, the difference in the performance of both of these, and they just then came up with this number, which was particularly suited to like differentiate between the performances of both the approaches, and like this like number should change, I guess, when like this code is released in this code base.
Maybe like we could ask in the PR.
Yeah.
And yeah, this also reminds me like you talked about some versioning kind of thing happening in Erlay. Do you know like?
Yeah, there For currently, there is only like the initial version, the version 1,
Yeah.
that we will be using. Or if there is a version that is lower than this, we would have to like reject that peer, because that we would like consider that peer to be malicious, because it is reconciling with a version that is not supported, I guess.
Okay, makes sense.
Like the reconciliation version can be greater than ours, but like it can also be lower than ours, but to a certain limit, and certainly not an invalid version.
So do they do they see the early protocol changing in version 2?
Like this is the like initial period, so only version 1 is used.
Yeah, makes sense. I was just curious, like why there's even a versioning kind of thing happening. Maybe they
Yeah,
just
like they might be thinking that uh, this protocol might need changes in the near future, and then that we should have a versioning system for this.
yeah, interesting.
Like also they use only this least recently used version, or like the least recently used cache system, where they could have used like other cache system also. I believe there is one also like an optimal one, and one kind of like randomly choosing which one to delete. Like, the most sense, LRU makes the most sense to be like used in Bitcoin Core, but they can be like they can make some custom implementation of an cache to like have a more optimal like kind of cache for like storing the witness transaction IDs.
I see. And this PR was like made into a draft because of like so many changes happening.
Yeah, the PR author now wants to add more. Like there are still being pieces of code adding being added in this PR, because there are some blockers. I guess I saw from the PR's status that there are some blockers in implementing this, and you can't like continue writing this PR until those blockers are solved. I
Oh,
guess there was a lot of activity just this past week, suddenly because of that.
oh. Were you able to join that IRC channel? I don't think I've joined.
No, I looked into it, but like, I was unable to like navigate kind of that IRC channel.
I see. No other questions from my side. It was a pretty informative session. Thanks for hosting.